What if I told you the entire universe was once smaller than a single atom? In the first trillionth of a second after the Big Bang, everything we know, galaxies, stars, even space itself, was compressed into a space so tiny it defies imagination. How did we go from that microscopic point to the vast cosmos we see today? The concept of before becomes meaningless when we approach the Big Bang. Time as we know it didn't exist in any recognizable form. Imagine standing at the North Pole and asking what's further north. The question itself makes no sense. Similarly, asking what came before the Big Bang is like asking what's north of the northernmost point on Earth. Our current physics reaches its limits when we try to probe these extreme conditions. The equations of general relativity break down at the singularity, where densities and temperatures become infinite. We don't have the mathematical tools to describe reality at this scale. There wasn't empty space waiting to be filled, nor a clock counting down to creation. Space and time emerged along with matter and energy in that explosive moment. This presents a profound paradox for human intuition. Every effect in our experience has a cause, but the Big Bang appears to be the ultimate exception. Some theories suggest quantum fluctuations in a primordial vacuum could have sparked the expansion, though we lack definitive evidence. Others propose time may have existed in a different form before our universe, like a higher dimensional surface our cosmos budded from. Visualizing this nothingness challenges our perception. It wasn't darkness. That would imply space existed. To be dark, it wasn't silence. Sound needs a medium to travel. This pre-existent state lacks any reference points we commonly use to describe reality. The rules of physics as we know them hadn't yet come into being. Even concepts like here and there had no meaning without space to define them. One approach to understanding is through the lens of quantum gravity, where space-time itself may have a granular structure at tiny scales. In this view, the Big Bang wasn't an explosion in space, but rather the beginning of space expanding outward. The whole universe could have emerged from a quantum fluctuation so minuscule it makes an atom look colossal by comparison. Scientists study this boundary by examining how particles behave in extreme conditions. In particle accelerators, we recreate fragments of that early energy, seeing how matter responds when subjected to temperatures approaching those initial moments. These experiments suggest the infant universe would have obeyed different physical laws. With forces now separate, like electromagnetism and the nuclear forces, potentially unified in a single superforce. The cosmic microwave background provides our best observational window into these early epochs. Its nearly uniform temperature across the sky implies the universe expanded faster than light could have traversed it, solving what physicists call the horizon problem. This remnant glow from when atoms first formed carries faint imprints of density variations that would later grow into galaxies. Some theories posit our universe might be one bubble in a multiverse foam, with other universes having different fundamental constants. In this scenario, the Big Bang marks the beginning of our particular bubble's expansion, not the absolute beginning of all existence. The lack of a conventional before might be an illusion stemming from our limited perspective. These ideas remain theoretical frontiers. We have no observational data from whatever preceded the Big Bang, if preceded even applies. The Planck epoch, the first 10 to the minus 43 seconds, remains veiled from our current investigative methods. Future breakthroughs in quantum gravity theories may provide better answers, but for now, this remains one of physics's deepest mysteries. What's remarkable is that we've traced cosmic history back so far at all. From this incomprehensible beginning emerged all the complexity we see around us, galaxies, stars, planets, and ultimately, life. Every atom in our bodies owes its existence to those first moments when the universe decided to become something rather than nothing. As we explore these ideas further, we find that ancient cultures had their own creation myths attempting to explain existence. Their stories, though different in detail, often shared this same sense of wonder about origins. The shift from mythology to modern cosmology represents one of humanity's greatest intellectual journeys, from storytelling to evidence-based understanding of our cosmic home. Long before telescopes and particle accelerators, civilizations looked up at the night sky and wondered how it all began. Ancient cultures developed creation myths that reflected their environment and values. The Egyptians saw the universe emerging from primordial waters, with the first land appearing as a mound, like the Nile's annual flooding, revealing fertile soil. The Norse envisioned a cosmic void called Ginnungagap, where fire and ice collided to form the first being. These stories weren't just fanciful tales, they served as frameworks for understanding humanity's place in the cosmos. What's striking is how many ancient cosmologies share common themes despite developing independently. Many describe creation emerging from nothingness or chaos. The Babylonian Enuma Elish tells of the universe forming from the split body of a primordial goddess. Chinese mythology speaks of Pangu hatching from a cosmic egg, his body parts becoming the physical world. These narratives reveal a universal human impulse to explain beginnings, even when lacking scientific tools. For thousands of years, this was how people made sense of celestial phenomena and natural cycles. The Greeks were among the first to move toward more systematic explanations. Thales proposed water as the fundamental substance, while Anaximander imagined an eternal boundless realm called the Apeiron. These early philosophers replaced gods with natural elements, though their ideas remained speculative. Aristotle later suggested a geocentric universe with crystalline spheres carrying celestial bodies, a model that would dominate Western thought for centuries. These transitionary theories bridged myth and early science, showing the first glimmers of empirical thinking about cosmic origins. By contrast, some indigenous cosmologies integrated creation with ongoing stewardship. Aboriginal Australian Dreamtime stories describe ancestral beings shaping the land, with the act of creation never truly complete. The Maya developed complex calendars tracking cosmic cycles they believed repeated over vast ages. These perspectives saw time as cyclical rather than linear, a concept modern physics now revisits when considering multiple Big Bangs or oscillating universes. The diversity of these ancient worldviews demonstrates how culture shapes our cosmic questions. Astronomy often featured prominently in ancient cosmologies, serving practical and spiritual purposes. The Babylonians mapped stars to predict events, developing mathematics to track planetary motions. Stonehenge aligned with solstices, showing Neolithic peoples recognized celestial patterns. Mesoamerican pyramids doubled as astronomical observatories and cosmic symbols. These structures reveal how early skywatchers connected earthly life with heavenly movements, long before understanding gravitational forces or nuclear fusion. Religion and science weren't separate domains in these early cosmologies. Hindu texts describe cosmic cycles lasting billions of years, remarkably close to modern estimates of the universe's age. The concept of multiverses appears in some Buddhist teachings. These traditions blended metaphysical speculation with detailed observations, creating frameworks that explained both celestial mechanics and human purpose. While details differ, they share our modern quest for a unified understanding of existence. Modern cosmology emerged when natural philosophers began prioritizing observation over tradition. The shift wasn't immediate. Galileo faced opposition for contradicting Aristotelian views with telescopic evidence. But the seeds were planted for evidence-based cosmic models that would eventually lead to the Big Bang theory. This transition marked a key moment when explanations required testable predictions rather than just compelling narratives. Ancient cosmologies show us alternative ways of conceptualizing space and time. Some African traditions viewed time as a spiral rather than a straight line. Polynesian navigators understood celestial navigation so thoroughly they could traverse vast oceans by starlight alone. These systems worked within their contexts, proving accurate enough for practical needs if not scientific, standards. They remind us that knowledge develops incrementally, building on earlier frameworks while correcting their limitations. The persistence of creation myths across cultures suggests something fundamental about human cognition. We're pattern-seeking creatures who prefer explanations to mysteries, even provisional ones. Modern science fulfills this same psychological need, but with methods that allow cumulative progress. Where ancient stargazers saw divine hands moving celestial spheres, we now understand gravitational mechanics, yet the sense of wonder remains familiar. By studying these ancient worldviews, we gain perspective on our own scientific journey. Contemporary cosmology continues some traditions while radically redefining others. We still seek origins, but with instruments that peer back to the universe's first light rather than relying on oral tradition. This progression from myth to measurement represents one of humanity's greatest intellectual achievements, the gradual replacement of storytelling with evidence gathering while preserving our innate curiosity about cosmic beginnings. The transition to modern astronomy came when thinkers began questioning assumptions rather than accepting tradition. This shift toward empirical methods would eventually lead to discoveries like Hubble's expanding universe and the cosmic microwave background, evidence requiring new explanations about cosmic origins. The stage was set for a revolutionary understanding of how everything began. In 1905, a patent clerk in Switzerland published papers that would rewrite the rules of the universe. Einstein's special theory of relativity introduced a radical idea: the speed of light remains constant for all observers, no matter how fast they're moving. This simple principle contradicted Newton's absolute space and time, which had stood unchallenged for over 2 centuries. Suddenly, measurements of length and duration became relative to the observer's motion. A clock on a fast-moving spaceship would tick slower than one on Earth, and the spaceship itself would appear slightly compressed in its direction of travel to an outside viewer. Newton's physics worked perfectly for everyday speeds but broke down when approaching light speed. Einstein realized space and time weren't separate fixed backgrounds but interwoven into a single flexible fabric called space-time. Gravity, rather than being a mysterious force acting at a distance, became the curvature of this fabric around massive objects. A planet orbits a star not because some invisible force pulls it, but because it follows the natural curves in space-time created by the star's mass. This vision transformed cosmology. Einstein's equations predicted a dynamic universe. Though he initially resisted this implication, his famous cosmological constant, later called his greatest blunder, was an attempt to keep the universe static within his theory, but the math clearly suggested space itself could expand or contract. When Hubble later observed galaxies moving apart, Einstein's equations provided the perfect framework to explain an evolving cosmos. The general theory also introduced astonishing new phenomena. Time flows slower in stronger gravitational fields, a fact confirmed by atomic clocks on airplanes running slightly faster than those on the ground. Near a black hole, this effect becomes extreme. An observer watching someone fall toward the event horizon would see their time slow to a crawl, while the falling person would experience normal time until reaching the deadly boundary. Relativity also predicted black holes, regions where space-time curvature becomes infinite. Matter compressed beyond a critical point collapses into a singularity, warping space-time so severely that not even light can escape. Initially debated as mathematical curiosities, these objects are now known to exist throughout the universe, with supermassive versions at galactic centers. Einstein's work changed how we measure cosmic distances. The bending of light around massive objects, gravitational lensing, allows astronomers to observe galaxies otherwise hidden behind foreground objects. This effect also lets us map dark matter by seeing how its gravity distorts light from background galaxies. Perhaps most remarkably, relativity showed energy and matter are interchangeable. The famous equation E equals mc squared revealed that a small amount of matter contains enormous energy, the principle behind both nuclear reactors and stars themselves. The sun shines because it converts matter to energy at its core, just one demonstration of relativity's profound implications. Yet Einstein's theories also set limits. They can't describe the universe's earliest moments when quantum effects dominated. The singularity at a black hole's center represents another breakdown point. Uniting relativity with quantum mechanics remains physics's greatest challenge, with string theory and loop quantum gravity as leading contenders. Relativity altered our cosmic perspective more than any theory since Copernicus. Space and time became plastic, responsive to matter and energy. Simple ideas like now became complicated. Two events simultaneous for one observer might occur at different times for another, moving relative to the first. The universe became stranger, yet more mathematically elegant. Einstein's equations also contained the seeds of modern cosmology. They allowed for solutions where space itself expands. Friedmann and Lemaitre would develop these into the first mathematical models of the Big Bang. Without relativity, we wouldn't have recognized the significance of Hubble's discovery that galaxies move apart, nor understood how to trace cosmic history backward to an explosive origin. The theory's predictions have survived every experimental test. From GPS satellites that must account for relativistic time dilation to the detection of gravitational waves, Einstein's vision continues proving its worth. These ripples in space-time, first observed a century after their prediction, offer new ways to study cosmic cataclysms like colliding black holes. Relativity didn't replace Newton's laws, but showed their limitations. For slow speeds and weak gravity, Newton's equations still work fine. But for understanding the cosmos at its grandest scales and most extreme conditions, we need Einstein's framework. His revolution revealed a universe far stranger than anyone imagined, one where time stretches, space bends, and matter tells space-time how to curve, while space-time tells matter how to move. Now we'll see how astronomers began putting these ideas to work, extending our cosmic vision beyond the Milky Way to discover that the universe isn't static, but expanding, a finding that set the stage for the Big Bang theory. In the 1920s, Edwin Hubble made observations that would permanently alter our understanding of the cosmos. Using the 100-inch Hooker telescope at Mount Wilson Observatory, then the largest in the world, he studied faint nebulae previously assumed to be within our Milky Way. His measurements revealed something astonishing. These nebulae were actually distant galaxies far beyond our own, each containing billions of stars. This discovery alone expanded the known universe by unimaginable scales, showing the Milky Way was just one island universe among countless others. Hubble noticed a peculiar pattern when analyzing light from these galaxies. Their spectral lines appeared shifted toward the red end of the spectrum, indicating they were moving away from us. More surprising was the correlation he found. The farther away a galaxy was, the faster it appeared to be receding. This relationship, now called Hubble's law, suggested space itself was expanding. It was as if the universe were a rising loaf of raisin bread, with galaxies as the raisins moving apart as the dough expanded. The implications were profound. If galaxies move apart over time, running the clock backward suggests everything was once compressed together. This provided the first observational hint of what would become the Big Bang theory. Hubble published his findings in 1929, presenting evidence that overturned the then dominant view of a static, unchanging universe. The data showed a clear linear relationship between distance and recessional velocity, a cornerstone of modern cosmology. Measuring galactic distances required innovative techniques. Hubble used Cepheid variable stars as cosmic yardsticks, stars whose regular pulsations reveal their intrinsic brightness. By comparing this known brightness to their observed dimness, he calculated their distances. For more remote galaxies beyond Cepheid detection, he relied on the apparent brightness of their brightest stars, or entire galactic luminosity. These methods, while imperfect by today's standards, established the foundation for measuring cosmic expansion. The scientific community resisted this radical interpretation. Many physicists, including Einstein, had assumed the universe was static. Einstein famously introduced his cosmological constant to maintain this view within his relativity equations. Other astronomers proposed alternative explanations for the redshift, suggesting light might lose energy over vast distances rather than indicating motion. The steady-state theory emerged as a competing model, postulating continuous creation of matter to maintain constant density in an expanding universe. Further observations strengthened Hubble's case. Additional measurements confirmed the redshift distance relationship held true for galaxies in all directions. No preferred center existed. Every observer would see other galaxies moving away as if they were at the center. This fit perfectly with Einstein's general relativity predictions of a dynamic, evolving cosmos. The universe wasn't expanding into anything. Space itself was stretching, carrying galaxies along with it. Critically, Hubble's work provided a way to estimate the universe's age. By measuring how fast galaxies recede and extrapolating backward, scientists could calculate when everything was compressed into an initial singularity. Hubble's original estimate of 2 billion years conflicted with geological evidence showing Earth was older, but refinements in distance measurements eventually resolved this discrepancy. The current estimate stands around 13.8 billion years. The expansion rate, now called the Hubble constant, remains a key parameter in cosmology. Determining its precise value requires measuring both distances and velocities of extremely remote objects. Modern techniques use supernovae as standard candles and exploit gravitational lensing effects. Different measurement methods initially produced slightly conflicting values, leading to the so-called Hubble tension that continues to intrigue cosmologists. Hubble's discovery fundamentally changed our cosmic perspective. The universe wasn't eternal and unchanging, but had a history and would continue evolving. This shifted cosmology from philosophical speculation to empirical science, where theories required observational testing. The expanding universe became the framework for understanding cosmic origins and destiny. Expansion also explained the observed darkness of the night sky, Olber's paradox. In an infinite static universe, every line of sight should eventually hit a star, making the night sky blindingly bright. Hubble showed space is finite in age, limiting how far we can see, and expansion stretches light's wavelength to lower energies. The expansion's uniformity on large scales became a key prediction for the Big Bang model. Later discovery of nearly uniform cosmic microwave background radiation provided strong confirmation. Together they showed space expands uniformly everywhere, like dots on an inflating balloon, all moving apart equivalently. Hubble never lived to see his discovery's full implications. Modern observations show expansion is accelerating due to mysterious dark energy, a phenomenon possibly related to Einstein's cosmological constant. This unexpected finding reveals we still don't fully understand cosmic dynamics. Hubble's work connected Einstein's theoretical framework with observable reality. It transformed how we study cosmic evolution, allowing us to trace the universe's history back to its hot, dense beginnings. Without this foundation, we wouldn't have recognized the significance of the cosmic microwave background or developed inflation theory to explain the universe's large-scale uniformity. Next, we'll examine how a Belgian priest-scientist took Hubble's observations to their logical conclusion, proposing the universe began as an explosive event from an ultra-dense state. Georges Lemaitre's primeval atom hypothesis faced considerable skepticism before becoming the foundation of modern Big Bang theory. In 1927, Georges Lemaitre proposed a radical solution to Hubble's expanding universe. The Belgian priest and physicist suggested the cosmos began as an ultra-dense primeval atom, a single point containing all matter and energy. His theory didn't just explain cosmic expansion, but traced it backward to an explosive origin. This was the first mathematical formulation of what would become the Big Bang theory. Most scientists of the era rejected Lemaitre's hypothesis. The prevailing view favored a steady-state universe, eternal and unchanging. A beginning in time smacked of religious creation myths, making physicists uneasy. Prominent astronomers like Fred Hoyle dismissed the idea as unscientific, coining the derisive term Big Bang during a BBC broadcast. The name stuck, though Hoyle meant it sarcastically. Lemaitre faced several specific objections. Critics argued his primeval atom violated thermodynamics. Energy couldn't simply appear from nothing. Others questioned how such an explosion could produce structured galaxies instead of pure chaos. Without direct evidence, the theory seemed speculative. Even Einstein initially resisted, telling Lemaitre, "Your math is correct, but your physics is abominable." The physics community preferred theories avoiding cosmic beginnings altogether. The priest-scientist built his case methodically. Combining Einstein's relativity equations with Hubble's observational data, he calculated the universe's expansion rate. Extrapolating backward, he estimated the initial event occurred roughly 20 billion years ago, remarkably close to current estimates. His 1931 paper described the primeval atom's disintegration as fireworks of unimaginable violence, predicting it would leave behind cosmic radiation. Few noticed Lemaitre's prediction about residual radiation at the time. The technology to detect it didn't exist yet. His ideas might have faded into obscurity had World War II not intervened. The conflict delayed scientific debates, allowing alternative theories to develop. The steady-state model gained followers by proposing continuous matter creation to maintain cosmic density during expansion. Lemaitre's dual identity as a Catholic priest fueled skepticism. Some physicists suspected religious motives, though his work remained strictly scientific. He carefully separated his theological views from his cosmology, stating, "There is no conflict between science and religion." Ironically, Pope Pius XII later misused the Big Bang theory as proof of divine creation, further alienating scientists. The primeval atom theory solved several puzzles simultaneously. It explained Hubble's recession data naturally. Galaxies move apart because space itself expands. It accounted for the universe's chemical composition, predicting vast amounts of hydrogen and helium from nuclear processes in the first minutes. And it provided a mechanism for galaxy formation, with density fluctuations in the early fireball seeding future structures. Lemaitre's least understood contribution involved the cosmological constant. While Einstein abandoned it as his greatest blunder, Lemaitre kept it in his equations. He argued it represented a repulsive force that might accelerate expansion, a prescient idea now central to dark energy research. This insight went unrecognized for decades. Critics raised valid scientific doubts. Without quantum gravity theory, no one could describe the singularity's physics. The tiny initial size strained credulity, all galaxies compressed into a volume smaller than an atom. And if the universe had a beginning, what caused it? These unanswered questions kept the steady-state model competitive through the 1950s. The tide turned with two developments. Improved telescopes confirmed Hubble's law held at greater distances, making continuous creation theories untenable. Then, in 1965, Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background, the cooled remnant of Lemaitre's primeval explosion. Its precise temperature matched Big Bang predictions perfectly. Subsequent observations cemented the theory's validity. Satellites measured minor fluctuations in the cosmic background, revealing density variations that became galaxies. Particle accelerators recreated early high-energy conditions, verifying how quarks combined into protons. The abundance of light elements matched calculations of nuclear fusion in the first 3 minutes. Lemaitre never lived to see full vindication. He died in 1966, just as the cosmic microwave background discovery transformed cosmology. Today his name appears alongside Hubble's in astronomy textbooks, though history often credits others for his insights. The Hubble-Lemaitre law now formally describes galactic redshifts, finally recognizing his equal contribution. The resistance to Lemaitre's theory reveals how science advances. New ideas face scrutiny until evidence overwhelms objections. What began as a fringe concept became the foundation of modern cosmology. His primeval atom theory didn't just explain cosmic expansion, it provided a framework for understanding the universe's entire history, from the first moments to the present day. This remnant radiation, Lemaitre predicted, would become our most powerful window into the early universe. The faint microwave glow holds clues about the cosmic dawn, revealing a time before stars or galaxies existed. The static on an old analog television contains a faint whisper from the birth of the universe. About 1% of that snow-like interference comes from cosmic microwave background radiation, the cooled remnant of the Big Bang's initial fireball. This invisible glow fills the entire cosmos, carrying information about the universe when it was just 380,000 years old. The discovery happened by accident in 1965. Researchers working with a sensitive horn antenna kept detecting persistent microwave noise coming equally from all directions. After eliminating all possible sources, from pigeon droppings in the antenna to terrestrial interference, they realized they'd found the predicted afterglow of cosmic creation. The radiation matched theoretical expectations precisely. The universe had cooled from billions of degrees to just 2.725 Kelvin above absolute zero. This radiation marks the moment the universe became transparent. Earlier than 380,000 years after the Big Bang, the cosmos was too hot and dense for light to travel freely. Protons and electrons formed an opaque plasma, constantly scattering photons. As expansion cooled the universe to about 3,000 Kelvin, electrons could finally combine with nuclei to form neutral hydrogen atoms. Light broke free, traveling across space, largely unimpeded for billions of years until reaching our detectors. The microwave background appears nearly uniform in all directions, one of cosmology's most significant findings. Temperatures vary by less than 1 part in 100,000 across the sky. This extreme uniformity suggested the early universe underwent extremely rapid expansion called inflation, explaining how regions now billions of light-years apart were once close together. Light-years apart share identical temperatures despite never having been in thermal contact. Tiny fluctuations in the background reveal where matter began clustering. Slightly denser regions appear as minute temperature variations. Areas where photons had to climb out of stronger gravitational fields lost more energy. These 0.001% differences became the seeds for galaxies and galaxy clusters. Without these primordial density variations, gravity would have had nothing to amplify, leaving the universe uniformly barren. Precision measurements required orbiting observatories above Earth's obscuring atmosphere. The COBE satellite in 1992 first confirmed the radiation followed a perfect blackbody spectrum, as predicted. Later missions like WMAP and Planck mapped the temperature variations with increasing detail, revealing the universe's geometry, composition, and expansion history encoded in the pattern of hot and cold spots. The background's polarization provides additional clues. As light scattered off electrons in the early plasma, it became slightly polarized, like sunlight reflecting off water. This polarization pattern reveals details about inflation and the universe's first split second of existence. It may also contain traces of primordial gravitational waves, ripples in spacetime, from the universe's violent birth. Surprisingly, the oldest light we can see doesn't come from the very beginning. The cosmic microwave background acts like a fog bank. We can see back to when the fog cleared, but not the fire that created it. The first few 100,000 years remain obscured by the primordial plasma's opacity. To peer further back requires indirect methods like studying particle interactions in accelerators that recreate early universe conditions. The radiation's temperature has cooled as the universe expanded. When first emitted, the light was in the visible spectrum, literally the universe's first sunrise. The stretching of space over billions of years redshifted this light into microwave frequencies. Future civilizations will see it redshifted even further as expansion continues. While remarkably uniform overall, subtle patterns in the microwave sky tell a detailed story. The precise distribution of hot and cold spots reveals the universe contains 5% ordinary matter, 27% dark matter, and 68% dark energy. This composition matches independent measurements from galaxy surveys and supernova observations, an interlocking web of evidence supporting our cosmic model. Some features challenge standard theories. Certain large-scale patterns appear improbably aligned in what physicists call the axis of evil. Other anomalies include unexpectedly cold spots and statistical asymmetries between hemispheres. While possibly just cosmic variants, these quirks keep scientists questioning whether we've missed something fundamental. The microwave background provides our most direct window into the early universe. Its discovery transformed cosmology from theoretical speculation into precision science. We now have detailed knowledge about cosmic composition, geometry, and evolution, all encoded in this faint radiation that permeates every cubic centimeter of space. This ancient light continues revealing surprises. Recent analysis suggests slightly different expansion rates depending on measurement methods, a discrepancy called the Hubble tension. Some propose this indicates new physics beyond our standard model. Others search for signs of previous universes in the polarization patterns, echoes of a cosmic cycle before our Big Bang. From a plasma-filled fireball to transparent cosmos, the universe's transition recorded in the microwave background represents one of nature's most important phase changes. We observe this event from within, like creatures formed from a cooled cloud, studying the condensation process that made them possible. The background connects us directly to universal beginnings, light emitted before Earth or the Sun existed, finally reaching our instruments after a 13 billion-year journey. The microwave background alone provides profound confirmation for the Big Bang theory, but additional evidence comes from studying how galaxies move away from us. The systematic redshift of distant objects matches what we'd expect in an expanding universe, another key piece of the cosmic puzzle. The light from distant galaxies carries an invisible fingerprint of cosmic expansion. As these galaxies move away from us, their light stretches to longer wavelengths, shifting toward the red end of the spectrum. This phenomenon, called redshift, occurs because space itself expands as light travels through it. The photons get stretched along with the fabric of spacetime. The greater the distance, the more the light has redshifted, providing direct evidence the universe grows larger over time. We measure this effect using spectroscopy. When astronomers split a galaxy's light into its component colors, they look for dark absorption lines, where elements like hydrogen or calcium absorb specific wavelengths. If these lines appear shifted from their laboratory positions, it indicates motion. The surprising consistency of redshifts across all directions suggests expansion happens uniformly throughout the cosmos. Every galaxy cluster appears to recede from every other, with no privileged center point. Space expands everywhere equally. The redshift distance relationship first noted by Hubble remains cosmology's bedrock. Modern observations confirm his original finding across billions of light years. Extremely distant galaxies show redshifts greater than 1, meaning their light has more than doubled in wavelength during its journey. Some of the earliest galaxies we observe emitted ultraviolet light that redshifted into infrared by the time it reached our telescopes. Without this expansion effect, their light would have remained invisible to our instruments. Redshift provides our primary method for mapping cosmic structure. By measuring how much galaxy light has stretched, we determine its recessional velocity. Combined with other distance indicators, this lets us construct three-dimensional maps showing the universe's large-scale structure, vast filaments and voids spanning hundreds of millions of light-years. These patterns emerged from tiny density fluctuations in the early universe, now revealed through systematic redshift surveys. Critically, redshift demonstrates space itself expands, not that galaxies move through space. Imagine dots on an inflating balloon. Each dot sees others recede, though none occupies a central position. Similarly, observers in any galaxy would measure redshifts consistent with universal expansion. This distinguishes cosmological redshift from Doppler shifts caused by local motion within space. Our Milky Way moves relative to the cosmic microwave background, producing a small additional Doppler component, but the dominant redshift comes from cosmic expansion. The stretching of light has observable consequences. As photons redshift, they lose energy. The universe effectively cools as it expands. Light emitted in the visible spectrum may arrive as infrared or radio waves after billions of years. This energy loss means distant galaxies appear fainter than their intrinsic brightness would suggest, an effect that must be accounted for when estimating cosmic distances. Redshift also provides a clock for cosmic events. Light from a galaxy with redshift 6 was emitted when the universe was about 1 billion years old. Objects at higher redshifts show us progressively earlier cosmic epochs. The current redshift record holders are galaxies and quasars observed shortly after the first stars formed, their light stretched by factors exceeding 10. These high redshift observations test our understanding of early structure formation and star birth. Not all redshift comes from expansion. Gravity also redshifts light climbing out of massive objects' potential wells, an effect confirmed near black holes and galaxy clusters. However, cosmological redshifts dominate on intergalactic scales. Combining these measurements reveals how mass distorts spacetime on both local and cosmic levels. The expansion rate derived from redshifts suggests the universe is about 13.8 billion years old. Different methods for measuring this rate now show slightly conflicting values, an issue called the Hubble tension. Some propose unknown physics may affect redshift interpretations at large distances. Others suggest systematic errors in distance measurement techniques. Resolving this discrepancy remains an active research area. Redshift observations led to the discovery of dark energy. Distant supernovae appear fainter than expansion rate predictions indicated, evidence that cosmic acceleration began about 5 billion years ago. This acceleration implies an unknown energy form counteracting gravity on large scales. The redshift-distance relationship remains our primary tool for studying dark energy's properties and evolution. Looking back through higher redshifts is like viewing cosmic history in reverse. Each increment takes us closer to the Big Bang, revealing how galaxies formed and evolved. Future telescopes aim to detect redshifts exceeding 20, probing the universe's first few 100 million years. These observations may reveal population 3 stars, the first generation of stars made purely from primordial hydrogen and helium. The stretching of light across cosmic time connects directly to the early universe. Photons from the cosmic microwave background exhibit redshifts around 1,100. Their wavelengths have stretched by a factor of 1,000 since emission. This ancient light and modern galaxy redshifts form complementary evidence for our expanding universe model. Together they tell a consistent story from the first atoms to the present day. The uniformity of redshifts in all directions strongly supports the cosmological principle, the idea that the universe looks roughly the same everywhere on large scales. No preferred direction or special location exists in the expanding cosmos. Measurements consistently show galaxies receding according to Hubble's law regardless of where we look. While redshift provides compelling evidence for expansion, other observations strengthen the case. The cosmic microwave background's temperature and spectrum, the abundance of light elements, and the large-scale distribution of galaxies all independently confirm the Big Bang model. Redshift ties these threads together by providing a continuous record of cosmic expansion from first light to the present. This brings us to another critical confirmation of the Big Bang, the precise amounts of hydrogen and helium found throughout the universe. These light elements formed in the first few minutes after expansion began, their abundances matching theoretical predictions with remarkable accuracy. The proportions we observe today provide direct evidence for high-energy processes in the early universe, further validating our cosmic origin story. The universe maintains a precise chemical fingerprint from its first 3 minutes. About 75% of ordinary matter exists as hydrogen, 25% as helium, with only trace amounts of heavier elements. This ratio matches exactly what nuclear physics predicts would form in the extreme heat of the early cosmos, a remarkable confirmation of Big Bang theory. Nuclear fusion only had a brief window to operate. Once expansion diluted matter enough, temperatures dropped below the threshold for fusing nuclei. The first protons and neutrons emerged around 1 second after the Big Bang, when the quark-gluon plasma cooled sufficiently. For the next 2 minutes, temperatures and densities allowed nuclear reactions to proceed. Scientists can calculate the expected element production precisely. At 1 second, the universe had cooled to about 10 billion Kelvin, hot enough to keep neutrons stable temporarily. During this narrow window, free neutrons could combine with protons to form deuterium nuclei. These deuterium nuclei could then fuse into helium-4, the most stable light nucleus. The process halted when temperatures fell below fusion thresholds, freezing in the element ratios we observe today. The abundance predictions depend critically on the photon-to-baryon ratio. For every proton or neutron, about 1 billion photons filled the early universe. This overwhelming photon bath influenced reaction rates. Fewer photons would have allowed more deuterium destruction, altering the entire element production chain. The observed abundances thus provide an independent measurement of this fundamental cosmic parameter. Deuterium deserves special attention. This heavy hydrogen isotope serves as a particularly sensitive cosmic probe. Its predicted abundance changes sharply with small variations in conditions. Observing deuterium levels in pristine gas clouds gives one of our most precise tests of these early universe calculations. Measurements match the predicted fraction of about 1 deuterium atom per 100,000 hydrogen atoms, strong evidence for the hot Big Bang model. The helium-4 fraction shows similar precision. Theory estimates about 25% of atomic mass should have converted to helium during primordial nucleosynthesis. Astronomical observations of ancient stars and gas clouds confirm this prediction to within 1%. More remarkable still, this helium formed in just 3 minutes, whereas stars would require billions of years to produce such quantities. Even the tiny amounts of lithium and beryllium provide valuable checks. These elements' predicted traces align with the rarest observations in ancient stellar atmospheres. The agreement holds over variations spanning 10 orders of magnitude, from abundant hydrogen to rare lithium isotopes. This consistent pattern across multiple elements bolsters confidence in our understanding. Alternative theories struggle to explain this fingerprint. Steady-state models require continuous element production, maintaining these exact ratios everywhere. They can't explain why oldest stars show slightly different compositions than cosmic averages. Evidence the primordial abundance pattern got slightly altered by later stellar processes. Only the Big Bang naturally accounts for both the initial pattern and subsequent evolutionary effects. The element ratios also constrain matter-antimatter asymmetry. For every billion matter-antimatter pairs that annihilated in the early universe, about 1 matter particle survived. This slight excess determined how many protons and neutrons were available to form atoms. Precision element measurements confirm this survival ratio with remarkable consistency. Our understanding has grown increasingly sophisticated. Modern computations account for hundreds of nuclear interaction pathways in the rapidly cooling plasma. They've correctly predicted subtle variations in helium-3 and lithium-7 abundances between different galactic environments, further validating the model. These calculations now incorporate neutrino interactions and quantum mechanical effects on reaction rates. Some tensions remain. The observed lithium-7 abundance falls about 3 times lower than predictions, an anomaly called the cosmological lithium problem. Possible explanations include unknown nuclear reactions or more exotic physics beyond standard models. Yet this single discrepancy coexists with multiple successful predictions, suggesting our understanding remains mostly correct, if incomplete. Element abundances provide independent confirmation of cosmic expansion history. The successful predictions about light elements mean the universe must have been substantially hotter and denser in the past. The required conditions precisely match those inferred from other evidence like the cosmic microwave background and galaxy redshifts, a coherent picture emerging from different lines of investigation. This chemical fingerprint remains visible billions of years later because stars inherited and built upon it. The first generations of stars formed from nearly pristine material, reflecting the primordial composition. Later generations incorporated heavier elements forged in stellar interiors, but still retained traces of the original mixture. Analyzing these ancient stellar atmospheres lets us effectively sample the early universe's chemistry. Some of the clearest measurements come from looking at the most distant quasars. Their absorption spectra reveal intervening gas clouds that have remained untouched since the universe's first billion years. These show the predicted element ratios with extraordinary precision, as if nature had intentionally preserved samples of the post-Big Bang material for our instruments to find. The agreement between prediction and observation spans scales from the entire visible universe down to individual atoms. Nuclear physics experiments on Earth confirm the same fusion processes would occur under early universe conditions. Particle accelerators reproduce temperatures last common when the cosmos was minutes old, demonstrating how neutrons and protons combine and separate. This evidence is particularly compelling because it's quantitative rather than qualitative. The predictions weren't approximate guesses. They were precise numerical constraints that subsequent observations matched precisely. Getting these numbers right speaks to how thoroughly we understand certain aspects of cosmic origins, even while major questions remain. With this elemental clock confirming the early universe's conditions, we can wind the cosmic film reel further backward to the first trillionth of a second when space expanded exponentially during the inflationary epoch. The smoothness and flatness of the universe we observe today stemmed from these earliest moments, when quantum fluctuations determined where galaxies would eventually form. The universe underwent its most dramatic transformation before most clocks could measure a single tick. In that first trillionth of a second, space expanded faster than light itself could travel, an exponential growth spurt called cosmic inflation. This wasn't expansion into anything. Space itself was stretching, smoothing out irregularities, and setting the stage for everything to come. Before inflation, all the universe's energy could have fit in a space smaller than a single atom at temperatures exceeding 10 to the 27th Kelvin. Under these conditions, the fundamental forces we know today, gravity, electromagnetism, and the nuclear forces, were unified into a single superforce. As the universe expanded and cooled, these forces separated out one by one, like phases of matter changing from gas to liquid to solid. The inflationary period solves several cosmic puzzles. The horizon problem, the fact that distant regions of space have identical temperatures despite never being in contact, finds its answer here. Inflation stretched microscopic quantum fluctuations across vast distances, creating slight density variations that later became galaxy clusters. These same fluctuations left imprints we now detect in the cosmic microwave background. For inflation to work, space had to expand by at least a factor of 10 to the 26th power in less than 10 to the negative 32nd power seconds. Imagine blowing up a marble to the size of the observable universe in that fraction of time. This extraordinary growth smoothed the cosmos to near-perfect uniformity, while simultaneously seeding the irregularities that allowed structure to form. Without inflation, the universe would look radically different today. Quantum effects dominated this epoch. The extremely small scale meant traditional notions of cause and effect broke down. Particles and energy flickered in and out of existence, their brief lives governed by uncertainty. These quantum fluctuations got frozen in as inflation stretched them to cosmic scales, becoming slightly denser regions that gravity would later amplify into galaxies. The energy driving inflation remains mysterious. Cosmologists call it the inflaton field, a hypothetical energy field that temporarily dominated the universe. When this field decayed, its energy transferred to ordinary particles, reheating the universe and beginning the hot Big Bang proper. This transfer marks the end of inflation and the start of the radiation-dominated era we can better understand through particle physics. Critically, inflation explains why the universe appears geometrically flat. Just as inflating a balloon smooths out wrinkles, cosmic expansion stretched spacetime to near-perfect flatness. Measurements of the cosmic microwave background confirm this flatness with remarkable precision, another successful prediction of inflation theory. The transition out of inflation wasn't perfectly uniform. Some regions stopped inflating sooner than others, potentially creating bubble universes with different physical constants. This idea, though speculative, leads to the multiverse hypothesis, the possibility our cosmos is one of many separate universes with different fundamental laws. After inflation ended, the universe filled with a quark-gluon plasma, an exotic state of matter where particles constantly formed and annihilated. Temperatures were so high that quarks and gluons, normally confined inside protons and neutrons, moved freely. This primordial soup existed for only microseconds before further cooling allowed composite particles to form. The energy scales involved surpass anything we can recreate experimentally. Our most powerful particle accelerators reach energies equivalent to about 10 to the 13th Kelvin, far short of inflation's 10 to the 27th. This limitation means we rely on cosmic observations to test theories about the universe's first moments. The detailed patterns in the cosmic microwave background serve as our primary evidence. Inflation also dictates the universe's ultimate fate. The initial expansion rate and matter distribution determine whether the cosmos will expand forever or eventually collapse. Current evidence suggests acceleration is increasing due to dark energy, a phenomenon that may relate to whatever caused inflation. The transition from quantum foam to structured cosmos happened with astonishing speed. In less time than it takes light to cross an atomic nucleus, the universe laid down patterns that would take billions of years to fully manifest. The largest structures we observe today, galactic superclusters stretching hundreds of millions of light-years, stem from quantum ripples magnified by inflation. While inflation theory explains many observations, it remains incomplete. We don't know what triggered it, why it lasted as long as it did, or how it connected to the subsequent hot Big Bang. Alternate theories exist, including bouncing universe models and emergent spacetime scenarios. Each makes testable predictions that future observations may confirm or rule out. The Planck epoch, the time before 10 to the minus 43 seconds, remains completely unobservable with current physics. Here, quantum fluctuations should affect spacetime itself, requiring a theory of quantum gravity we don't yet possess. String theory and loop quantum gravity attempt to describe this regime, but experimental verification is challenging without energies approaching the Planck scale. Cosmic inflation represents our best current explanation for the universe's large-scale structure and uniformity. Like all good scientific theories, it makes precise predictions that observations can test. Each new measurement of the cosmic microwave background or distribution of galaxies provides another opportunity to confirm or modify our understanding. The echoes of inflation surround us. Every galaxy, every star, every atom owes its existence to quantum fluctuations stretched across cosmic distances during those first instants. What began as microscopic randomness became the framework for all structure in the universe, a remarkable transformation from inchoate energy to organized matter. As space-time stretched during inflation, it carried tiny irregularities forward like ripples frozen in an expanding pond. These became the primordial seeds for structure, the slight overdensities where gravity would eventually concentrate matter into galaxies. The exact pattern of these fluctuations determines where galaxy clusters formed billions of years later. This connection between quantum mechanics and cosmic structure represents one of science's most profound insights. Events at the smallest scales imaginable dictated the arrangement of the largest structures we can observe. The universe's vast complexity arises from simple rules operating at extremes of energy and scale. With inflation setting the initial conditions, the stage was prepared for particle formation. The first stable protons and neutrons would soon emerge from the cooling quark-gluon plasma, beginning the process of building atoms and eventually stars. The transition from energy to matter marked the next critical phase in cosmic history. Imagine two regions of the universe so far apart that light hasn't had time to travel between them since the Big Bang, yet they share identical temperatures and properties. This is the horizon problem. How do distant parts of the cosmos coordinate without ever being in contact? The cosmic microwave background reveals this puzzling uniformity. Opposite sides of the observable universe show matching temperatures to within 0.001%, despite being separated by over 90 billion light-years. In conventional Big Bang models without inflation, these regions would never have interacted. Their uniformity would require impossible coordination in early cosmic history. Inflation solves this by providing a mechanism for superluminal expansion. Before inflation, the entire observable universe occupied a microscopic region small enough to reach thermal equilibrium. Then space expanded exponentially, stretching this uniform patch to cosmic scales in less than 10 to the negative 32nd seconds. This explains why widely separated regions share properties. They were once neighbors in that tiny pre-inflation volume. The expansion wasn't through space, but of space itself. Imagine dots on a balloon's surface moving apart as it inflates. Each dot sees others recede, though none moves through the balloon's surface. Inflation stretches microscopic quantum fluctuations into cosmic scale density variations, the seeds for galaxy formation. The process simultaneously smooths irregularities while imprinting the patterns that would later grow under gravity. Evidence for inflation comes from several precise predictions. It accounts for the universe's observed flatness. Inflation stretches any initial curvature to near-perfect flatness, like zooming in on a sphere until it looks flat. Measurements confirm space is flat to within 1% accuracy. Inflation also predicts the specific pattern of temperature fluctuations seen in the cosmic microwave background, another successful match with observations. The theory explains why we don't see certain hypothetical relics like magnetic monopoles. In standard Big Bang cosmology, these particles should be abundant, but inflation would have diluted them to negligible concentrations, effectively wiping them from the observable universe while preserving their quantum fluctuations as cosmic structure seeds. Inflation's energy source remains theoretical, often modeled as a hypothetical inflaton field. When this field's potential energy dominated the universe, it caused gravitational repulsion that drove exponential expansion. As the field decayed, it transferred energy to ordinary particles, a process called reheating that initiated the hot Big Bang phase we can better describe with particle physics. The quantum fluctuations that became galaxies originated as microscopic variations in the inflaton field. Regions where the field took slightly longer to decay ended up with more energy density after inflation. These minute differences, about 1 part in 100,000, were stretched to cosmic scales and eventually amplified by gravity into today's web of galaxies and galaxy clusters. Cosmic inflation makes several testable predictions. It suggests the universe should appear perfectly flat on large scales, confirmed by measurements of the cosmic microwave background. It predicts a nearly scale-invariant spectrum of density fluctuations, also matching observations. The theory anticipates specific patterns in the polarization of the cosmic microwave background that future observations could detect. Alternate theories without inflation struggle to explain the horizon problem and flatness. Some propose varying speed of light scenarios, but these lack inflation's predictive successes. Others suggest the universe didn't begin with a singularity, but emerged from some prior state, ideas that may eventually harmonize with inflation rather than replace it. The stretching of space-time during inflation would have generated gravitational waves, ripples in space-time's fabric. These primordial waves should leave a distinct imprint on the polarization pattern of the cosmic microwave background. Detecting this signature would provide strong additional evidence for inflation and help constrain different inflationary models. Inflation naturally leads to the idea of a multiverse. If inflation continues eternally in some regions while stopping in others, different bubble universes could form with varying physical constants. Our observable universe might be one such bubble within a much larger multiverse, a speculative but intriguing possibility that emerges naturally from inflationary cosmology. The transition out of inflation remains poorly understood. How exactly the inflaton field decayed into ordinary particles, a process called reheating, determined the initial conditions for the subsequent hot Big Bang. Different reheating scenarios would affect details like the primordial element abundances and the exact spectrum of density fluctuations. While inflation explains much, questions remain about its exact mechanism and what preceded it. Some theories attempt to unify inflation with quantum gravity by proposing it emerged from some quantum geometric state. Others suggest inflation might cycle through phases of expansion and contraction, quite different from standard eternal inflation models. Future observations could refine our understanding. More precise measurements of the cosmic microwave background polarization might reveal the gravitational wave signature of inflation. Large-scale galaxy surveys could detect subtle patterns imprinted by inflationary physics. And theoretical work continues to explore how inflation might emerge from more fundamental theories of quantum gravity. The success of inflation lies in its elegant solutions to multiple cosmic puzzles, from horizon and flatness problems to structure formation. It provides a framework where microscopic quantum effects can influence cosmic scale structure, connecting the very small with the very large. The theory continues to guide our exploration of the universe's earliest moments while suggesting new questions about ultimate origins. From this inflationary foundation, the universe transitioned to the more familiar hot Big Bang phase. The primordial plasma that filled space after reheating would soon give rise to the first stable particles, the building blocks of atoms and ultimately galaxies. The transition marked the end of exponential expansion and the beginning of the universe's gradual cooling and structure formation. For 380,000 years after the Big Bang, the universe remained completely opaque, a searing plasma too hot for light to travel freely. Then, within a span of about 100,000 years, everything changed. As temperatures dropped below 3,000 Kelvin, electrons slowed enough to be captured by atomic nuclei in an event called recombination. This process formed the first stable hydrogen and helium atoms, scattering light that had been trapped in the plasma and rendering the universe transparent for the first time. The transition happened universally across space. One moment, photons couldn't travel far without colliding with free electrons, like light diffusing through thick fog. The next, space became clear enough for light to travel nearly unimpeded across cosmic distances. This relic light, now redshifted to microwave frequencies, forms the cosmic microwave background we detect today, a snapshot of the moment when light broke free. Before recombination, protons and electrons existed as separate charged particles in a state called ionized plasma. This soup of charged particles constantly scattered photons, making the universe opaque. The energy of each interaction kept atoms from forming, Electrons had too much kinetic energy to remain bound to nuclei. Temperatures needed to cool sufficiently for electromagnetic forces to overcome particle motions. This cooling occurred as the universe expanded. Space stretched by a factor of about 1,000 during this epoch, diluting both matter and photon densities. The photon energy decreased proportionally as their wavelengths stretched. By around 380,000 years post-Big Bang, average temperatures reached where electrons could stably orbit nuclei, first forming simple hydrogen atoms with single protons and electrons. The shift happened relatively quickly in cosmic terms. Though spanning 100,000 years, this was merely 0.002% of the universe's current age. The exact timing depended on matter density and expansion rate, parameters we've measured precisely from the cosmic microwave background. These measurements confirm recombination occurred when the universe was about 1/1000th its current size. Recombination didn't happen instantaneously everywhere. Denser regions took slightly longer to cool below the ionization threshold. These differences left subtle temperature variations in the cosmic microwave background, the seeds for future structure formation. Areas where recombination occurred earlier released photons at slightly higher temperatures, patterns that eventually grew into galaxy clusters. The newly formed atoms were almost entirely hydrogen and helium, the only elements produced in significant quantities during Big Bang nucleosynthesis. About 75% of atoms were hydrogen, 25% helium by mass. Trace amounts of lithium and deuterium also formed, but heavier elements wouldn't exist until stars started fusing them billions of years later. The liberated photons began their nearly unimpeded journey across space. These same photons, now redshifted by a factor of 1,100, form the 2.725 Kelvin cosmic microwave background we detect today. Their near-perfect blackbody spectrum, one of the most precise matches ever measured in nature, confirms they originated from thermal equilibrium at recombination. This transition marks the earliest event we can directly observe. The cosmic microwave background provides our furthest observational window into the past, looking back to when the universe was only 0.003% its current age. Earlier epochs remain obscured by the opaque plasma that preceded recombination. Interestingly, the transparency wasn't perfect. Some regions remained partially ionized, particularly near early quasars and hot stars that formed later. Neutral hydrogen clouds also absorbed certain wavelengths, leaving characteristic absorption lines we can study. But overall, the universe became transparent enough for light to travel freely on large scales, a critical threshold for cosmic evolution. The process didn't just reveal photons, it shaped them. As light climbed out of gravitational potential wells around denser regions, it lost energy through gravitational redshift. This Sachs-Wolf effect imprinted subtle temperature variations that encode information about matter distribution at recombination. These patterns have been mapped with increasing precision by satellites like COBE, WMAP, and Planck. Recombination also affected the universe's sound waves. The plasma had supported acoustic oscillations, pressure waves propagating through the hot gas. When atoms formed, these waves froze in place, leaving characteristic peaks in the cosmic microwave background's angular power spectrum. The spacing of these peaks reveals the universe's geometry and composition with remarkable precision. The transition had lasting consequences for structure formation. Neutral hydrogen atoms could now clump under gravity without being disrupted by photon pressure. These overdensities eventually collapsed to form the first stars and galaxies, a process that took hundreds of millions of years but began with recombination's clearing of the cosmic fog. Curiously, the universe wouldn't stay completely transparent. Later, energetic radiation from the first stars and quasars would reionize much of the intergalactic medium, but by then, cosmic expansion had diluted matter enough that transparency persisted despite renewed ionization. This second transition occurred between 150 million and 1 billion years after the Big Bang. Today we study this event through multiple methods. The cosmic microwave background provides a direct image. Quasar absorption spectra show intervening hydrogen clouds that formed shortly after recombination, and simulations recreate the complex interplay of particles and radiation during this critical transition, validating our understanding of the physics involved. Recombination represents one of the most important phase changes in cosmic history, the moment when matter and radiation decoupled, allowing light its first uninterrupted journey across space. The universe transformed from an opaque plasma to a transparent expanse within a cosmic blink, setting the stage for all structures that would follow. With stable atoms now formed, the universe entered what cosmologists call the Dark Ages, a period before the first stars ignited, when only neutral hydrogen gas and the fading afterglow of recombination filled the cosmos. The next great transition would come when gravity pulled matter together into structures dense enough for nuclear fusion to begin, lighting up the universe again after hundreds of millions of years of darkness. The question of what caused the Big Bang takes us beyond established physics into theoretical frontiers. Our best theories extend back to the Planck epoch, 10 to the minus 43 seconds after the initial event, but the moment of creation itself remains unexplained. Modern cosmology approaches this mystery through several competing frameworks, each with distinct implications for whether our universe is unique or one of many. Quantum physics suggests empty space isn't truly empty, but seethes with virtual particles flashing in and out of existence. Some theories propose our universe began as one such quantum fluctuation in some primordial state. The zero-energy universe hypothesis argues the positive energy of matter perfectly balances gravity's negative energy, meaning the cosmos could have emerged from nothing without violating conservation laws. While compelling, these ideas remain untested speculation. Inflationary models offer another perspective. Eternal inflation suggests space continually generates new universes through quantum fluctuations in an ever-expanding multiverse. Each bubble universe could have different physical constants, meaning our life-friendly parameters might be one possibility among countless others. This would answer why our universe seems fine-tuned for life without invoking design. In a multiverse, all possibilities eventually occur. String theory introduces the concept of brains, higher dimensional membranes that could collide, transferring immense energy. These collisions might seed new universes in cycles of creation. Our Big Bang could represent one such collision in an eternal sequence with no beginning or end. The theory predicts such events would leave imprints in the cosmic microwave background, though none have been definitively detected. Loop quantum gravity proposes a different origin. In this framework, space has a discrete, granular structure at tiny scales. Following quantum principles, a previous universe could have contracted to a minimum size before bouncing into expansion, avoiding the singularity problem. This cyclic model implies an endless sequence of universes with no first cause needed. The lack of a clear cause doesn't mean the Big Bang violated physics. Our current understanding simply breaks down at the singularity. Just as quantum mechanics resolved classical physics failures at atomic scales, a theory of quantum gravity may eventually explain cosmic origins. Until then, we work with plausible hypotheses constrained by known physics. Multiverse theories face criticism for being untestable. If other universes exist beyond our cosmic horizon, we can never observe them directly. Some researchers argue this makes multiverses more philosophy than science. Others counter that certain models make testable predictions, like specific patterns in the cosmic microwave background, that future telescopes might detect. The concept of before the Big Bang may not apply in conventional terms. If time began with our universe, asking what preceded it could be meaningless, like asking what's north of the North Pole. Some theories treat time as emergent rather than fundamental, suggesting it crystallized after the universe's first moments, just as ice forms from water. Uncertainty about the Big Bang's cause doesn't undermine the theory's validity. The evidence for cosmic expansion, nucleosynthesis, and microwave background remains robust regardless of ultimate origins. Similarly, Darwin's theory of evolution stands firm, while abiogenesis research continues. Questions about life's beginning don't invalidate natural selection. Current experiments attempt to probe these extreme conditions indirectly. Particle colliders recreate energies near those of the early universe, though still far short of Planck's scale. Observations of gravitational waves might reveal signatures of cosmic strings or other remnants from creation. And precision measurements of the microwave background continue searching for clues about inflation or cyclic models. The hard problem remains time's origin. Even in bounce or multiverse scenarios, some initial state must exist. Religious traditions often posit a creator, while scientific approaches seek natural processes. This boundary between science and metaphysics will likely persist until new theoretical frameworks emerge, just as quantum mechanics revolutionized atomic-scale physics. The possibility of other universes raises profound questions. If physical constants vary across multiverses, does that make our life-permitting parameters special or inevitable? Some researchers argue intelligent observers can only exist in universes with stable matter and long-lived stars, an anthropic explanation for our universe's apparent fine-tuning. Future telescopes might find evidence supporting specific origin theories. The James Webb Space Telescope could detect anomalies in early galaxy formation, hinting at pre-Big Bang conditions. Next-generation cosmic microwave experiments may uncover signs of bubble universe collisions or other multiverse imprints. Or we may find our universe appears remarkably alone. The answer may require unifying quantum mechanics with gravity, physics' greatest unsolved problem. Current quantum gravity theories like string theory or loop quantum cosmology suggest space and time could emerge from more fundamental structures. In these frameworks, the Big Bang represents a phased transition rather than absolute beginning. Our limited view also complicates the search. We observe only part of the universe within our cosmic horizon, regions so distant light hasn't reached us yet. The full cosmos could be vastly larger than what we see, containing structures or evidence currently beyond observation. Future light from these regions may carry new clues. The nature of dark energy adds another wrinkle. If this mysterious force accelerating cosmic expansion relates to the inflaton field, it might connect to the Big Bang's origin. Alternatively, dark energy could represent a new fundamental field that will eventually trigger another phase transition, perhaps spawning new universes. Until more evidence emerges, the Big Bang's cause remains cosmology's ultimate question. Whether our universe is alone or part of a vaster multiverse, its existence raises deep philosophical and scientific issues. The answer will likely require conceptual breakthroughs we can't yet imagine, just as quantum theory revolutionized physics a century ago. With these open questions about cosmic origins, we naturally ponder the universe's ultimate fate. Will expansion continue indefinitely, or could some yet unknown force reverse it? Current observations point toward an accelerating expansion driven by dark energy, a phenomenon that might determine not just our future, but whether new universes could ever arise from ours. The story continues as we search for answers in the faint whispers of cosmic background radiation, the subtle motions of distant galaxies, and the high-energy collisions of particle accelerators. Each provides another piece of the puzzle, bringing us closer to understanding the biggest question of all: how everything we know came to exist. The universe we can see, stars, galaxies, gas clouds, makes up less than 5% of what's actually out there. The rest consists of two mysterious components: dark matter and dark energy. These invisible forces shaped cosmic evolution from the Big Bang onward, yet we still don't know what they are. Dark matter first revealed itself through its gravitational pull. In the 1930s, astronomers noticed galaxies spinning faster than visible matter could explain. Later studies of galaxy clusters showed they contained far more mass than their stars and gas accounted for. This missing mass doesn't emit or absorb light, hence dark, but its gravity binds galaxies together and molds the cosmic web. The cosmic microwave background provides crucial evidence. Its temperature patterns show how matter clustered in the early universe. The observed structures require 5 times more matter than we can see. Without dark matter's extra gravity, galaxies would never have formed in the time available. The universe would be mostly smooth with few stars or planets. We've mapped dark matter's distribution using gravitational lensing. As light passes massive objects, their gravity bends its path. By measuring distortions in background galaxies, astronomers reconstruct dark matter's location. It forms an intricate web spanning billions of light years, with galaxies forming at its densest nodes. Despite extensive searches, dark matter's identity remains unknown. Leading candidates include WIMPs, weakly interacting massive particles, or axions, hypothetical lightweight particles. Experiments in deep underground labs attempt to detect these particles directly. Others study high-energy collisions that might produce them. So far, no confirmed detections exist. Dark energy presents an even deeper mystery. In the late 1990s, astronomers found distant supernovae were fainter than expected. The universe's expansion wasn't slowing down as gravity should dictate, it was accelerating. Some unknown force was pushing space apart faster over time. This repulsive effect, dubbed dark energy, makes up about 68% of the universe's energy content. Einstein's cosmological constant offers one explanation. He originally introduced this term to keep the universe static, later calling it his greatest blunder. But if this constant represents dark energy's unchanging density, it perfectly explains the acceleration. Quantum physics predicts vacuum energy that could match this description, though calculations give values 120 orders of magnitude too large. Alternative theories propose dynamic dark energy fields that change over time. Some models suggest our understanding of gravity might be incomplete on cosmic scales. These ideas all face significant challenges. The simplest cosmological constant model still fits current data best. Dark energy became dominant relatively recently in cosmic history. For the universe's first 9 billion years, matter's gravity slowed expansion. Around 5 billion years ago, dark energy's repulsive effect surpassed gravity's pull, beginning the current epoch of accelerating expansion. Future observations aim to determine whether dark energy's strength varies, which would rule out the cosmological constant. These mysteries connect directly to the Big Bang. Dark matter's gravity enabled galaxies to form from primordial density fluctuations. Without it, structure formation would have progressed too slowly. Dark energy determines the universe's ultimate fate, whether expansion continues forever or eventually reverses. Together they control cosmic evolution from start to finish. The search for dark matter intersects with particle physics. If it consists of undiscovered particles, they likely formed in the hot early universe alongside protons and electrons. Their relics today could reveal conditions moments after the Big Bang. Some theories unify dark matter with other puzzles, suggesting it might relate to neutrinos or extra dimensions. Dark energy raises deeper questions about space itself. Vacuum energy concepts stem from quantum field theory, but their cosmic implications remain unclear. Some speculate dark energy could cause a big rip, tearing atoms apart far in the future. Others suggest it might fluctuate, potentially triggering new cosmic cycles. Current experiments narrow the possibilities. The Dark Energy Survey and upcoming Euclid telescope map galaxies across cosmic time, tracking how expansion accelerates. The L-Lug Zeppelin experiment seeks dark matter particles in ultra-sensitive detectors shielded from cosmic rays. These efforts gradually rule out theoretical options while hunting decisive evidence. The cosmic microwave background holds clues about both mysteries. Its detailed polarization patterns might reveal dark matter's early interactions. Subtle distortions could show how dark energy behaved during the universe's first billion years. Future experiments aim to measure these signals with unprecedented precision. These unknowns highlight how much we still don't understand about our universe. All visible matter, every star, planet, and galaxy, represents just a tiny fraction of what exists. The majority consists of substances we can't directly detect, only infer through their gravitational effects on cosmic scales. Progress comes through multiple approaches. Particle accelerators recreate high-energy conditions similar to the early universe. Astronomical surveys map the large-scale structure shaped by dark matter and dark energy. Together, they provide complementary ways to test theories about these elusive components. The Big Bang set the initial conditions, but dark matter and dark energy determined what happened next. One sculpted the cosmic web, while the other controls its ultimate fate. Solving these mysteries would complete our understanding of cosmic history from the first moments to the distant future. As research continues, we're reminded how much remains beyond our current knowledge. The universe's composition challenges our assumptions about matter, energy, and gravity. Future discoveries may require fundamentally new physics, perhaps connections between quantum mechanics and gravity that also explain the Big Bang itself. These hidden components continue shaping the universe today. Dark matter's gravity pulls galaxies together, even as dark energy pushes space apart. Their competing effects will determine whether the cosmos ends in heat death, a big crunch, or some more exotic fate. The story that began with the Big Bang still has many chapters left to unfold. From this invisible framework emerges everything we can see: the stars, planets, and ourselves. The search for dark matter and dark energy isn't just about filling gaps in our knowledge. It's about understanding the fundamental nature of reality and our place within it. With these mysteries still unsolved, we turn to considering the universe's possible futures. Will expansion continue indefinitely, or could dark energy's properties change over time? Current evidence points toward a cold, empty end, the Big Freeze, but the full story depends on the true nature of these unseen cosmic components. Tracing the universe's future requires understanding its expansion. Current observations show this expansion accelerating due to dark energy, a discovery that overturned previous assumptions about cosmic destiny. The fate of everything hinges on how this mysterious force behaves over time. The leading scenario is the Big Freeze, also called heat death. If dark energy remains constant, represented by Einstein's cosmological constant, expansion will continue indefinitely. Galaxies outside our local group will accelerate away until their light becomes too redshifted to detect. Stars will exhaust their fuel over trillions of years, leaving behind stellar corpses and black holes. Eventually, even black holes evaporate via Hawking radiation, leaving only diffuse particles in an ever-expanding void where temperatures approach absolute zero. In this cold, dark, empty universe, all thermodynamic free energy dissipates, ending the possibility of organized structures or life. A more violent possibility is the Big Rip. If dark energy's repulsive force strengthens over time, called phantom energy, it could eventually overcome all binding forces. First galaxy clusters would separate, then individual galaxies. About 3 months before the end, phantom energy would rip apart solar systems. Planets would detach from stars in the last minutes. Atoms themselves would be torn apart in the final 10 to the minus 19 seconds as the cosmic scale factor becomes infinite. This scenario requires dark energy density to increase with time, a possibility not currently supported by observations, but not yet ruled out. The Big Crunch presents the most symmetrical alternative. Expansion reverses into contraction. This requires dark energy to weaken sufficiently for gravity to overcome it, causing space to start collapsing. The cosmic microwave background temperature would rise as photons blue shift. Galaxies would merge as space contracts, eventually cramming all matter back together. Temperatures soar until atoms dissociate into quark-gluon plasma, essentially reversing the Big Bang. Some theories propose this collapse could trigger a new Big Bang, creating a cyclic universe without true beginning or end. Current evidence disfavors this scenario as expansion continues accelerating rather than slowing. The rate of acceleration holds the key. Precise measurements track how expansion changes over cosmic time. Supernova surveys show dark energy behaving like a cosmological constant so far, its density appearing constant as space expands, but small deviations could emerge over longer periods. Future projects like the Vera Rubin Observatory will measure millions of supernovae across 10 billion years of cosmic history, testing whether dark energy's strength varies. Other exotic possibilities exist. Vacuum decay could occur if our universe resides in a false vacuum state. A quantum fluctuation might create a bubble of lower energy vacuum that expands at light speed, rewriting fundamental constants as it passes. This would abruptly change physics without warning. Chemistry and even atomic structure could become impossible. Though highly speculative, such an event would be catastrophic and unavoidable. Another model suggests the universe could eventually enter a de Sitter state, exponentially expanding empty space where even black holes have evaporated. Quantum fluctuations might then spawn new universes in isolated pockets, effectively reproducing inflationary cosmology on vastly longer timescales. This connects to multiverse theories, where our cosmos is one among countless ephemeral bubbles. The timeline for these scenarios spans incomprehensible durations. The stellar era, when stars still shine, lasts perhaps 100 trillion years. The degenerate era of cooling stellar remnants persists for 10 to the 40 years. Black holes dominate for up to 10 to the 100 years before evaporating. The dark era that follows continues essentially forever, as expansion dilutes remaining particles to infinite separation. These timescales dwarf the universe's current 13.8 billion-year age. Dark matter plays a role too. Its gravitational pull works against expansion, though measurements confirm dark energy already dominates. If dark energy weakens while dark matter remains constant, gravity could eventually reverse expansion. Some modified gravity theories propose dark energy and dark matter represent different manifestations of spacetime's unknown properties, potentially changing our understanding of cosmic fate. The size of the observable universe constantly shrinks in practical terms. As expansion accelerates, light from distant objects can no longer reach us. We already see this effect. Galaxies at the current cosmic event horizon appear frozen in time as their light stretches to infinite wavelengths. In about 150 billion years, all galaxies beyond our local group will be invisible, their light redshifted beyond detection. Future civilizations would perceive the universe as far emptier than we do. Current evidence strongly favors the Big Freeze scenario. Multiple independent measurements, from supernovae to baryon acoustic oscillations, converge on constant dark energy density. Unless this changes, heat death appears inevitable. Yet mysteries remain. Why does dark energy's density take its particular value? A deeper understanding may reveal connections to quantum gravity or other undiscovered physics. The fate of the universe ultimately depends on dark energy's true nature, whether it's truly constant or variable, whether it connects to vacuum energy or represents something entirely different. As we gather more precise measurements, we test theories that might explain why the cosmos is expanding as it is, and where this accelerating journey ultimately leads. From this grand cosmic perspective, we turn finally to considering our own place in the universe. We are temporary inhabitants of a small planet, living during that brief epoch when stars still shine and matter organizes itself into complex forms. This cosmic context frames the philosophical significance of our existence within the vast sweep of time from Big Bang to whatever future awaits. We are stardust that has learned to observe itself. Every atom in our bodies was forged in the hearts of stars that lived and died before our solar system formed. The carbon in our cells, the oxygen we breathe, the iron in our blood, all were created in stellar furnaces, then scattered across space by supernovae. We are the universe made conscious, temporary configurations of matter that can contemplate its own origins. The cosmic perspective humbles us. Our entire observable universe contains about 2 trillion galaxies, each with billions of stars. Our Milky Way is one among countless others, and our Sun, an ordinary star, orbiting about halfway out from its center. Earth occupies no special position, just one rocky planet among billions in our galaxy alone. The Copernican principle keeps demonstrating we're not central to anything but our own experience. Yet this vastness doesn't diminish our significance. It changes the nature of significance itself. For all we know, Earth may harbor the only intelligent life in the observable universe, or it may be one among countless inhabited worlds. Either possibility carries profound implications. If we're alone, we bear unique responsibility as cosmic witnesses. If not, we're part of a much larger story still unfolding. Our moment in cosmic time is fleeting but privileged. The universe has been habitable for about 10 billion years and could remain so for trillions more. Yet intelligent life likely couldn't have emerged much earlier. The first stars lacked heavy elements necessary for planets like Earth. We live during the brief stellar era when main sequence stars still burn before expansion dilutes matter beyond useful concentration. The same physics that govern galaxies operate in our bodies. The electromagnetic force binding atoms into molecules enables our chemistry. Gravity's weakness allows complex structures without constant collapse. Even the expansion rate matters, slightly faster, and no galaxies form, slightly slower, and the universe recollapses before life appears. Our very existence depends on precise cosmic parameters. Science brings these truths to light through methodical observation. Unlike ancient myths that placed humans at the center of creation, modern cosmology reveals our genuine place, spectators to an ancient, vast universe not made for us. This realization could be frightening, but many find it strangely comforting. There's dignity in accepting reality as it is, rather than as we might wish. Our growing cosmic awareness reflects a profound shift in perspective. 5 centuries ago, we thought Earth was the center of creation. Now we know we orbit an average star in an unremarkable galaxy, observing just a fraction of all that exists. This journey from centrality to cosmic insignificance ironically reveals our most remarkable trait, the capacity to understand the universe that made us. The atoms-turned-astronomer's paradox captures this beautifully. Matter organized itself into creatures that can study matter. After billions of years of cosmic evolution, the universe developed the ability to observe and question itself. In that sense, We represent one way the universe knows itself, through our eyes, telescopes, and scientific instruments. This perspective transforms how we view daily life. Personal conflicts and societal problems shrink when considered against cosmic timescales. Yet individual existence gains depth when recognized as a rare opportunity, matter temporarily arranged to experience and understand. The same forces that shaped galaxies operate in each breath we take. Our technology extends this understanding further. Telescopes act as time machines, showing distant galaxies as they were billions of years ago. Particle colliders recreate early universe conditions on microscopic scales. We've developed tools to study phenomena across 40 orders of magnitude, from quantum fluctuations to galactic superclusters. The universe's age and size could overwhelm us, but they also connect us to something grand. Every action becomes part of cosmic history. The energy in our bodies was present at the Big Bang, transformed through generations of stars, now powering thought itself. We're not separate from the universe. We're its current manifestation in human form. Scientifically literate civilizations likely develop similar perspectives. Any beings discovering their cosmic context would face the same humbling realizations about scale and time. This shared understanding could form the basis for interstellar communication, a common framework transcending biology or culture. The cosmic view also suggests ethical implications. If Earth is rare or unique in fostering life, preserving it becomes a universal responsibility. The same applies to humanity's potential. We may represent the universe's best chance to understand itself in our galactic neighborhood. Wasting that opportunity would be tragic on a cosmic scale. Looking outward changes how we see our planet. From space, national borders disappear. Human conflicts appear as minor disturbances on a fragile biosphere. The overview effect reported by astronauts describes this shift in perception, seeing Earth as a small, beautiful, and isolated world needing protection. Our cosmic journey continues as new discoveries refine our place in the universe. Dark matter and dark energy remind us most of reality remains unknown. Exoplanet studies may soon tell us how common life is. Each revelation adjusts our self-understanding while raising new questions about existence's ultimate nature. Philosophically, the Big Bang challenges notions of purpose. If the universe began naturally without external cause, meaning isn't built into cosmic structure, but created by conscious beings within it. This makes human purpose more precious, not granted by some external source, but chosen and nurtured through our actions and understanding. The most profound scientific revolutions share a common thread. They remove humanity from a privileged position while revealing our capacity to understand deep truths. From Copernicus to Darwin to Hubble, each breakthrough expanded the universe while making our place within it more understandable. Knowledge replaces centrality with connection. We're made of star stuff, pondering stars. This cosmic context frames our brief moment of awareness. We live during the universe's springtime, after the first stars ignited, but before the last ones fade. On geological timescales, we're newcomers, yet we've unlocked secrets spanning nearly the entire cosmic history. That ability gives our era special significance in the grand story of existence. As we continue studying the cosmos, the story grows richer. New telescopes will reveal fainter, more distant objects. Space missions will explore potentially habitable worlds. Particle experiments may uncover dark matter or new physical laws. Each discovery writes another chapter in humanity's growing understanding of its cosmic home. The journey from cosmic ignorance to awareness spans mere centuries scientifically, but represents an immense leap in self-understanding. We've progressed from earthbound observers to cosmic mapmakers, tracing universal history back to its first moments while pondering its ultimate fate. This knowledge doesn't isolate us. It grounds us in physical reality while expanding what's possible to imagine. Standing between quantum and cosmological scales, we occupy a middle realm where atoms assemble into conscious beings. That we can comprehend both the very small and very large suggests our minds are tuned to reality's fundamental rhythms. The same laws governing supernovae and galaxies operate in our cells and thoughts. We are the universe thinking about itself. This brings us to our current moment, where decades of cosmic discovery meet accelerating technological change. We're reaching a threshold where humanity's future may extend beyond Earth, carrying our cosmic perspective to new worlds. The story that began with the Big Bang continues through each choice that preserves and expands conscious understanding in our corner of the universe. As the story continues, we remain both spectators and participants, observers of cosmic grandeur and shapers of Earth's future. Our greatest achievements may lie in balancing these roles, appreciating universal vastness while acting locally to nurture life and understanding. The cosmic perspective doesn't reduce human concerns, but frames them within the grandest context possible. We've traced the universe from a microscopic point to the vast cosmos we see today. Energy transformed into matter, atoms formed from plasma, and gravity-sculpted galaxies from quantum fluctuations. Dark matter shaped this structure while dark energy now drives expansion. The same physics that govern stars operate in our cells. The Big Bang reveals existence as emergent rather than fixed. Meaning comes not from cosmic design, but from matter's capacity to organize and reflect. Our understanding remains incomplete. Dark energy's nature, quantum gravity's rules, and the initial singularity still puzzle us. The universe continues evolving, and so does our comprehension of it.